Okay, good morning children. Today here we are going to discuss the conversion of chemical, rather electric energy to chemical energy. We can convert electrical energy to chemical energy, and the cell in which it takes place, the cell in which we can do this thing, electrical energy to chemical energy, it is called electrolytic cell. So in electrolytic cell, we can convert electric energy into chemical energy. Remember, in case of galvanic cell, chemical energy was changed to electric energy. Okay, now let us consider a first case. Suppose we have a container where we have here molten NaCl. Sodium chloride is an ionic compound. It has to be heated to a very high temperature to make it molten. Remember, there is no water here, and we have two plates, and they are connected to source of current. This is the minus end of battery, this is plus end of battery. Okay, now this is electrolytic cell. In electrolytic cell, this minus plate is called cathode, and this plus plate is called anode in case of electrolytic cell. Now, since sodium chloride is an ionic compound, there will be lot of sodium ion, chloride ion. Here there are plenty of sodium ion, chloride ion. So when we are passing current, all sodium ion will move towards the negative plate, cathode, and all chloride ion will move towards the positive plate, anode. So what changes happens at the cathode and anode after they go that side, and we are going to write it down now. So at cathode, now this is going to happen, Na plus will gain an electron from this plate and form sodium. So there will be deposition of sodium here, deposition of sodium. Sodium, you can write here deposited. And at anode, what is going to happen is Cl minus arrow, Cl plus electron. Chloride ion will come here and it will lose an electron and form chlorine atom. Now chlorine atom cannot exist freely. So chlorine atom will combine in pair and it will form what? Cl2 gas. So we will get chlorine gas here and sodium deposited. So we see what is happening, you see, is that sodium chloride is getting broken down into the constituent element. And this phenomenon of breaking down of a compound by passing electric current, is called electrolysis. So we are discussing the phenomenon of electrolysis. The phenomenon of electrolysis takes place in a electrolytic cell. But remember, like galvanic cell, reduction takes place at cathode, even here. Oxidation takes place at anode, even here. Okay, now if we had here, if we had aqueous sodium chloride, then what is going to happen? Aqueous sodium chloride, because you see, when we have aqueous sodium chloride, there is Na plus, there is Cl minus, there will also be some H plus that comes from water. There is also OH minus, there is also water. So all these are present here. So now what is going to happen at cathode now? At cathode, we know positive ions migrate towards cathode. So this is a positive ion, this is a positive ion. So this can go and get reacted, this can react. So let me write down both the possibilities. Na plus electron, Na. At cathode this can happen like here, or this can happen, H plus electron, H. H plus C, H. Now since you know hydrogen atom cannot exist freely, so we can write here half H2. So there is two possibility at the cathode. So we can say there is a competition between Na plus and H plus. There is a competition. But which one will actually happen? You know, one which has more reduction potential, that is going to happen. Now reduction potential of sodium, you know, its value is minus 2.71 volts around, whereas reduction potential of hydrogen, you know, is 0 volt. So reduction potential of hydrogen is much more. So you know, it is this thing that is going to happen. It is this thing that is going to happen. This thing is not going to happen when we consider aqueous NaCl. Now one more thing here, you know, since this H plus is actually obtained from water. This H plus is actually obtained from water. So you see, we can, if we add these two equations, then what happens is this H plus cancel. So H2O plus electron, half H2 plus OH minus. Or to get rid of this fraction, we can multiply both by 2. So 2 H2O plus 2 electron, arrow H2 gaseous plus OH minus, 2OH minus aqueous. This is liquid. So we can say this is what that happens at the cathode when we are considering aqueous sodium chloride solution. Okay, now what about anode? What about anode? Now at anode, you know, which is positively charged, we have to consider the negative ion. So which one is the negative ion here? Cl minus and OH minus. So two possible thing at the anode will be Cl minus forming Cl plus electron, Cl minus forming Cl plus electron, and to balance it, here we can write half Cl2 because chlorine atom doesn't exist freely. So Cl minus aqueous is giving half Cl2 gas electron. So this can happen at the anode. Another possibility is this OH minus. This OH minus which can lose electron and form OH. So this is the hydroxyl ion is a hydroxyl group. And then this OH also which does not exist freely, then what happens is this 4 OH, 4 OH combine together and it forms 2 water plus O2. So, if we can combine this, before we combine these two, let us multiply this by 4, because here we have 4 OH. This OH is coming from here. So this one and this one will cancel, and I am writing it here. The process taking place at anode. So it will be 4 OH minus arrow 2 H2O plus O2 plus 4 electron. So this can happen at the anode. So you see there are two possibilities. One is formation of chlorine, another is formation of O2. But which one will happen? Which one is going to happen? Now, since at cathode we have seen, I said one which has more reduction potential, that happens. And as far as anode is concerned, one which has less reduction potential, that happens. Or we can say in another way, one which has more oxidation potential, that happens. So at the cathode, one which has more reduction potential, that happens, and at the anode, one which has more oxidation potential, or we can say one which has less reduction potential, that happens. Okay, now if you see the oxidation potential value, if you see, that OH minus has more oxidation potential. OH minus has more oxidation potential than Cl minus. If you see the table, you will get this one. OH minus has more oxidation potential than Cl minus. So, this one is expected to happen. So we should expect to get at the anode, oxygen gas. We should expect to get oxygen gas at the anode. But this like this in this case it doesn't happen. It doesn't happen in this case. It is because a reason that we say it is because It is because there are two ways we can say this process. This process we say it's a kinetically very slow process. Kinetically very slow. This process OH minus, it's a very very slow process. We have, in next chapter we have about a rate of chemical reaction, that is chemical kinetics, that we will be considering. Now this process is a very slow process, kinetically is very slow, and that's why, for this to happen, we need more voltage. We need more voltage. We need, we can say, since we need more voltage, that's why this process does not take place. So why this process does not take place, even if it has more oxidation potential? It is because it is kinetically very slow, or we can say the reason for this, a phenomenon called over voltage. Over voltage, due to over voltage, this process does not take place. So we will not get oxygen. We will not get oxygen at the anode. So what will happen at the anode? It is this that will happen at the anode. So when aqueous NaCl is localized, we will get hydrogen gas at the cathode, we will get chlorine gas at the anode, and there will be another product. There will be another product. How another product? It is, we will also get in the solution, we will also get another product as NaOH. How NaOH will get? Because you see here, this Na plus is remaining in the solution. Na plus is remaining in the solution, and you see your OH minus also is remaining in the solution. So that Na plus and OH minus, will form NaOH. So electrolysis of aqueous NaCl, we get hydrogen gas at the cathode, and we get oxygen gas. Sorry, this doesn't happen. We get chlorine gas at the anode. In addition, we get what? Sodium hydroxide. The reason why this process, in spite of it having more oxidation potential, doesn't happen, because, as I already said, it is a kinetically slow process, and there it requires more voltage for oxygen. This phenomenon is called over voltage. That's why it doesn't happen. Okay. Now, another case of electrolysis we need to discuss. One is your aqueous copper sulfate solution. Electrolysis of aqueous copper sulfate solution. This is another very important thing. Now there are two cases here. Number one case is using platinum inert electrodes. So let us first consider this, then there is another case. So we have here say copper sulfate solution, and we have here a platinum rod. This is also platinum rod, and this is connected to source of current. So this is minus, this is plus. Minus is called cathode and plus is called anode. So here there are many ions here. There is copper plus 2 ion, there is sulfate ion, there is H plus, there is OH minus here. So ultimately what happens in the cathode? What happens in the cathode? So at the cathode, this is one possibility, and the other possibility is H plus electron, half H2. Now we know that one which has more reduction potential, that happens. Now reduction potential of copper is much more than hydrogen. Copper value is 0.34 volts, so it is this one that will happen. So here we get copper at the cathode. This one will not happen. At the anode, here what happens is it is it is water that gets involved. I mean this OH minus that is here, that is going to react at the anode. This one which was not happening here, that happens here. So OH minus forming this, this thing that happens at the anode. So let me write down 4 OH minus arrow 2 H2O plus O2 plus 4 J2. This happens at the anode. So we get copper, deposition of copper at the cathode, and we get oxygen gas at the anode. In case of electrolysis of aqueous copper sulfate using platinum electrodes.